Good morning, one and all. Welcome to my PPT. In this PPT, we are going to discuss the subject probability and statistics. And before entering into PPT, let me introduce myself. My name is Bhuvneshwar. Currently pursuing my undergraduate from Institute of Aeronautical Engineering in Computer Science and Engineering Department. Basically, I belongs to A section. You can see my roll number on the screen. Without further delay, let us move into the PPT. Okay. Today the topic which was assigned to me was random vectors and the probability function which was assigned to me. You can see on the screen random vectors and its probability functions. Okay, we will move. Basically the whole PPT consists of the contents like, see, you can first we will going to discuss about the random vectors. Then further, without delay, next we will go to the expectations. After finding the expectations, we go to the correlation and covariance of the matrix. Later, properties of the covariance matrix, and at last we are going to discuss the function of random vectors, the method of transformations. In this whole PPT, I can assure that you are going to consider this all topics and you will be get perfection in this topic which was chosen. Okay, we will go to the introduction next. Here basically random vectors, the first slide which I taken to into my PPT was random vectors. Like you guys should first understand what are the random vectors and the random variables. I will try to explain you in the detail what are the random variables. As you can see on my screen that random variables, when dealing with multiple random variables, it is sometimes useful to use vector and matrix notations. This makes the formula more compact, and let us use the facts from linear algebra in this section. We briefly explore the avenue. The reader should be familiar with matrix algebra before reading this section. When we have n random variables x1, x2, xn, we can put them in a vector x. This slide looks like somewhat big, but we can explain the short. Like if you take a random vector x1, x2, xn as elements, corresponding elements, then we can make a random vector as x1, x2, xn. We can put them in a vector. This whole slide deals with this point. Now we will move into the other slide. 1 minute. Here in the picture you can see that x is equal to x1, x2, x3. Basically this you can observe from the matrix basic definition. It is a column vector where only one column is present, where it's denoted by capital X, and each one of the element is denoted with capital X corresponding to its number x1, x2, x3 up to xn. We call x a random vector. Here x is an n dimension vector because it consists of n random variables. This PPT we usually use bold capital letters such as x. Like bold, we can use anything like a, b, c, p, q, or like here it's for my convenience I am using x, y, z to represent a random vector. To show the possible value of random vector, we usually use bold lowercase letters such as x, y, z. Thus we can write the CDF of random vectors as f capital X, subnotation of x is equal to f of x1 comma x2 up to xn, where x1, x2, x3 is equal to p of probability. Here p nothing but a probability function. Probability function, we know that we can write like any number of terms. x1 is less than x1, x2, like here x1, capital X1, which I said before, capital X denotes the random vector, and small x here you can see on my screen, like small vector denotes this, like x1 is less than, capital X1 is less than small x1, capital X2 is less than small x2. Upon going on, capital Xn is less than or equal to small xn. Here the main important point you have to know that it's not the less than, it's less than or equal to. If the xi's are joined continuous, the PDF of x, PDF means probability distribution function. Here in my PPT I used this like symbolic representations. PDF means, remember that, probability distribution function of x can be written as f of x is equal to f of x1 into x2 comma x1 upon x1 comma x2 comma xn. Okay, I hope so you understood this whole PPT. This is the basic information which we are going to discuss in the further slides. We will move on to the further slides. Here I will try to explain you how to calculate the expectation of some given variable. See, the expected value vector expected value vector or mean vector of a random vector x is defined as, basically we represent the expectation with capital E. Expectation is nothing but mean. We can assume that mean, but if it's not the every case, most of the cases expectation is nothing but mean. E, let's multiply E with the x. Ex is equal to, so here if we multiply x with a column matrix, in matrix we know that every matrix will get, if we multiply a constant with the matrix, every element of the matrix get corresponding multiplied with the constant. Here the same formula applicable, here I applied the same formula. E is multiplied with every element of the column matrix, then it's become ex1 ex2 upon ex1 for the each and element. Similarly, a random matrix is a matrix whose elements are random variables. In particular, we can have m by n random matrix M as capital. We see capital M here too. I denoted the main matrices with the capital letters and subordinate coordinate elements with small letters, and corresponding elements as x11 x12 upon x1n to xmn. Here the matrix has order mn. It's the main point that the matrix has order mn. I think so you know about the order. Order is nothing but row multiplied by column. It's a simple, just not a big deal. Okay, we'll move on to the further slide. We sometimes write this as capital M is equal to x of ij, which means that xij is the element in the ith row and jth column of M. The mean matrix M is given by em is equal to, here expectation is multiplied with the mean, then it gives to em, where the corresponding elements of the matrix are ex double one, like double one, it's not row multiplied by column ex11, don't call it a double one, it's 11. Next corresponding elements ex12 upon ex1n, and the last limits goes to exmn, where m is the number of rows and n is the number of columns. So last elements is, and here see before the last limit is xmn, where we multiplied with e as a constant, then the last element become as exm. If like it's not like it's a small thing, like I can't explain briefly like how you got. Linearity of expectation is also valid for random vectors and matrices. In particular, let x be an n-dimension random vector and the vector of y be defined as, let us define a capital Y variable as y is equal to a. Here is capital A and multiplied with capital X plus small b. Here the small b is one of the coefficient. Let us define a small coefficient to remove the collinearity, and let us define another variable called capital A. Linearity of expectation is also valid for random vectors and matrices. In particular, x be an n-dimension random vector and a random vector y be defined as y is equal to ax plus b. For the future use, let's take it as equation 1. Please remind the equation y is equal to ax plus b. It's not like it's your wish to remind or not. Like for the basic information, let us suppose to remind for this whole ppt y is equal to ax plus b, where a is a fixed m by n matrix and b is a fixed m dimension vector. See here a is a fixed, here both a and b are fixed for a particular matrix. See here a is a non-random m by n matrix and b is a fixed m dimension vector. Then we have e of I is equal to a e x plus b. Also x1 x2 up to xk are n dimension random vectors. Then we have e of x1 plus x2 plus xk is equal to ex1 plus ex2 upon e of xk. I hope so you understand this slides too. Now we came into the heart of the PPT, like the correlation covariance matrix. Correlation and covariance matrix. For a random vector x, we define the correlation matrix Rx as Rx is equal to expectation of x into x transpose. X transpose is nothing but just transpose every row into column and just interchange the row into column interchange, then you can get the transpose matrix. For the people who don't know how to do the transpose is nothing but just interchange the rows and columns with respect to corresponding elements, then you will get transpose matrix. Just transpose the x matrix, then you will get x transpose. Then we can define R of x, where Rx is a correlation matrix. R of x is equal to expectation of x into x transpose is equal to then we will get the corresponding elements like x1 square x1 x2 upon x1 xn. This is the first row, and further moving on to the second row, we can get like elements x2 x1 x2 square x2 x3 upon x2 xn. At the further, at the last continuation, like a last row is xn row, right? Like there you can get xn x1 xn x2 upon xn whole square. Like diagonal limits are corresponding multiplied elements like x1 square x2 square x3 square x4 square x4 x5 square going on xn square. Like corresponding elements are like x1 natural numbers multiply whole square. Then if you further simplify, or if you multiply e into, if you take the e outside the matrix into inside the matrix, you can multiply every element with e. Then it will become e x1 square, e of x1 x2, e of x1 xn for the first row, and e of x2 x1, e of x2 square up to e of e is expectation of x2 xn for the second row. If you consider the last row, then it will become e of xn x1 for the first element and e of x2 xn x2 for the second element upon e of xn square. Even here the corresponding principal diagonal elements x1 square x2 square x3 square upon natural numbers continue going on expectation of e of xn square. Okay, where T shows that matrix. Okay, before I discuss that, here I wrote as a main point where T shows matrix transpose. Okay, I discussed before, I think so. Okay, we will move on to the further slide. Okay, here in the slide, c of x equal to e of whole bracket x minus ex multiplied with x minus ex whole transpose. Just here what we did is we subtracted ex minus x and whole transpose the matrix e of x. See here, C of ఇంకో 10 minutes డిస్టర్బ్ చేయకన్నా ప్లీజ్. రాకు మధ్యలో నా ఫోన్లో స్టోరేజ్ కూడా లేదు, ఎప్పుడూ అయిపోయింది నాకు తెలియదు ఈ వీడియో. నువ్వు అలా డిస్టర్బ్ చేసావు అనుకో, మళ్ళీ స్టోరేజ్ కూడా లేదు అసలుకి. Okay, leave this guys, we will concentrate on our PPT. See here, c of x equal to e of whole bracket, like we just subtract x minus e of x which we got earlier and whole transpose that, and we get x minus e of x whole transpose matrix. Just simply multiply those matrix, the resultant matrix will be shown on the screen. You can see like variance of, like we know that expectation of x subtracted from the capital X which gives the variance and covariance. Here the first matrix became the x1. Here we take here variance and second element as covariance, because if we multiply the same element we will get the variance. If we multiply the different elements, like relation between the different terms or variables, then each variance of each element is dependent on second variable, right? So here the concept applicable here, and the remaining elements will get the covariance, not the variance, and the principal diagonal elements has variance. Remember the point. The covariance matrix is a generalization of the variance of a random variable or random vector. Remember that of a random variable we have variance of x is equal to ex square minus e of x square. The following example extends for the formula of random vectors even. We can expand this formula to even the random vectors, not only for the random variables. Even this formula we can use anywhere, like nature like symmetry, right? Like we can apply this formula to for even the vectors, not only for the variables. Here for the reference you can prefer these examples which I gave in my PPT. You can look, like I will erase my screen. Wait, like you can see, like wait, here's example 6.11, example 6.22. You can refer this like examples to know the like calculation parts for this. Like some people may get confused about the theory and they can do the sum. Like these people can refer these examples to solve the problems. I will try to solve the first example for a random vector x shown, where c of x is equal to rx minus e of x multiplied with e of x whole transpose. This is the vector given. Then solution is correlation matrix of x. Rx is equal to e of x into x transpose covariance matrix of x is equal to C of x is equal to E of x minus Ex into x minus Ex whole transpose is equal to Rx minus E of x whole transpose. Okay, second example, you can see, I will share my PPT, you can then later you can see the example. I am skipping the example for this part of time. Here now we came into another part of our PPT called properties of covariance matrix. This is another main part of the PPT, properties of covariance matrix. You can see on my screen. The covariance matrix is a generalization of the variance of random vectors. It is an important matrix and is used extensively. It's mark the word extensively. Let's take a moment and discuss its properties. Here we use concept from linear algebra such as eigenvalues and positive definitives. First, note that for any random vector x, the covariance matrix Cx is symmetric matrix. This is one of the main important. Note that covariance matrix for every covariance matrix Cx, is like it should be symmetric for the covariance matrix. This vice versa is not true. Remember the point, vice versa shouldn't be true, but covariance matrix C of x should be like symmetric matrix. Like basic definition of symmetric matrix is A into A transpose is equal to 1. Like A is equal to A transpose. We can take the example like A is equal to A transpose. We can declare it as a symmetric matrix. This is because of C of x is equal to C of ij. C of ij is equal to covariance of xi xj is equal to covariance of xj comma xi cj. Thus the covariance matrix has all the nice properties of symmetric matrix. In particular, C of x can be diagonalized and all the eigenvalues of Cx are real. Here we assume x is a real random vector. The xi can only take real values. A special important property of covariance matrix is that it is positive semi-definite. Here in the PPT we are going to see PSD means positive semi-definite. Here in the slide also M is said to be the positive definite PD for all vectors B is not equal to 0. We have B transpose multiplied with capital M multiplied with small b greater than 0. By the above definition we note that every PD matrix is also PSD, but converse is not generally true. Here we show the covariance matrix are always PSD. Here this theorem gives satisfactory explanation for the above theorem mentioned before I had mentioned. Let us consider x be a random vector with n elements. Then the covariance matrix Cx is a positive semi-definite PSD. Proof, I think so. Proof is not that important. If you want, you can go through the proof I mentioned in the PPT, right? Like I don't explain the proof here. If you want, you can go to the proof in the PPT. I am for the time variant, I am skipping the proof. If you any of you guys you want, you can take over my PPT and you can you can go through the proof. For time variant, I am skipping the proof. Now we will discuss the function of random vectors, the method of transformations. A function of a random vector is a random vector. Thus the method that we discussed regarding functions of two random variables can be used to find distribution of functions of random vectors. For example, we can state a more general form of theorem 5.1 which was mentioned earlier. Let us first explain the method of and see some examples on how to use it. Let x be an n-dimensional random vector with joint PD of f of x. Let g tends to r power n which gives rise to rn, being continuous invertible function with continuous partial derivative, and h, let define a new variable h which is g inverse. Suppose that the random vector y is given by y is equal to g of x, and thus x is equal to g inverse y is equal to h of y, such that x is equal to, which we discussed earlier, x1 x2 x3 up to xn, this is a column matrix, and which gives rise to h1 of y1 y2 y3 comma yn, and the last row h of n can be declared as y1 comma y2 comma yn. The PDF of f of y can be given by f y1 y2 yn. Okay. Here the PDF of y, f of y1 yn is given by fy of y is equal to f of x hy modulus of j. Modulus means that like positive will become negative, negative will also positive. Here the j is equal to det of, you can raise me a question that what is j? J is nothing but det of determinant of partial differentiation of h1 with respect to partial derivative of y1, partial derivative of h1 with respect to partial derivative of y2, go on partial derivative of h1 with respect to partial derivative of y of n, and the last row partial derivative of hn with respect to partial derivative of y1, which gives rise to last limit as partial derivative of hn derivative of partial y power n, and we can finally evaluate it as y1 comma y2 comma yn. Here normal Gaussian random vectors. Here I am going to discuss about the normal Gaussian vectors. We discussed two jointly random variables previously in section like before slides. In particular, two random variables x and y are said to be bivariate normal joint normal if ax plus in the form of ax plus by has normal distribution for all a comma b belongs to R. We can extend the definition of n jointly normal random variables. Random variables x1 comma x2 comma xn are said to be jointly normal if all a1 comma a2 comma an, then random vector a of x1 plus a2 x2 plus upon an xn is a normal random variable. As before, we agree that the constant 0 is a normal random variable with 0 mean and variance, n of 0 comma 0, where we have several jointly normal random variable. We often put them in a vector. The resulting random vector is called a random Gaussian random vector. Like normal is we can call as Gaussian. Before we studied in early of our schooling days, even like normal can always called as Gaussian from the other language. We can either call normal random vector or Gaussian random vector. A random vector x gives rise to x1 xn x upon xn is said to be a normal or Gaussian if the random variables x1 comma xn up to xn are jointly normal. And to find the general form of PDF of a Gaussian random vector, it is convenient to start from the simplest case where the xi are independent and identity distributed. Xi such that n of 0 comma 1, in this case we know how to find the joint PDF. If it is simply a product of individual PDFs, let's call such random vector is standard normal random vector. So let z is equal to, let's define a new vector z which belongs to basically a column matrix z1 z2 upon zn, where zi's are id and z1 is similar collinear like n of 0 comma 1. We got these four functions. Like try to remember this last function 1 by 2 pi whole power n by 2 exponential of 1 power minus 2 z transpose into z. For standard normal random vector, z and zi dash are z1 similar to n of 0 comma 1, and PDF is given by fz of z is equal to 1 by, like the formula which I said to remember, the same formula here. Now we need to extend the formula to general normal random vector with the m and covariance matrix C, the very similar to which we define general form of a random vector from the standard normal random vector. We remember that if z belongs similar to n of 0 comma 1, the random vector x, this the main part of the heart of the equation, x is equal to summation of z plus mu has n mu comma summation square, which is nothing but standard deviation. Z square, like summation square is not, we know from the basic, like it's a standard deviation formula distribution. We would like to do same thing for the normal random vectors. Assume that I have a normal random vector x with the mean m and covariance matrix C. We write x similar to n of m comma c. Further, assuming the C is a positive definite matrix, the positive definiteness assumption here does not create any limitation. We already know C is a positive and semi-definite. We also know C positive definite and is only if determinant of C is greater than 0. So here we only exclude the case C is equal to 0. If det of C is equal to 0, then you can show that you can write some xi linear combination of others. So indeed we can remove them from the vector without losing any information. Then from linear algebra, we know that there exists an n by n matrix Q such that Q into Q transport is equal to I. Like Q into Q, this is nothing but I is an identity matrix where every element is 0 and corresponding principal diagonal elements are equal to 1. Then we can call it an identity matrix. C is equal to Q into D into Q transpose, where D is an diagonal matrix. D is equal to D1 1, like it's an diagonal matrix, every element belongs to 0 and corresponding elements are d1 1 comma d2 2 upon last element is dn. The positive definiteness assumption guarantees that du's are positive. Let's define d1 like root of d is equal to, like we will multiply every, we know, like if you multiply the capital D with root 2, then every multi corresponding to the d vector will be given under root. We have d square is equal to d. At finally we get the equation a into a transpose equal to a transpose into a is equal to c. Now we have ready to define the transformation that converts the. So here you can see a into a transpose into a is equal to c. Now we can finally conclude that c of x is equal to a cz a transpose. Finally a is equal to a transpose since cz is equal to I. Thus we have shown that x as a random vector with mean m and covariance c. Now we can use this example 6.15, like this example, to find the PDF of x such that f of x is equal to 1 by modulus of determinant of a multiplied with fz function of a inverse whole, like take like variable which its take is x minus m, where m is the covariance, is equal to 1 by 2 pi whole power n det of a exponential 1 minus 1 by n a inverse x minus n whole transpose a inverse x minus m. Like finally after like doing the mathematical part and conversion, we get the final excuse me 1 by 2 pi whole power n by n under root of det of c exponential minus 1 by n x minus m t c power minus 1 x minus m bracket for normal random vector x with m and covariance matrix C. The PDF is given. Like for this final step we had derived this whole part. F of x, this is final equation, 1 by 2 pi whole power n by n under root of determinant of c exponential of minus 1 by n x minus m whole transpose c inverse x minus m. Like it's in the form of diagonalization of matrix. This is the final equation for the normal relation vector x with mean and covariance c. PDF is given by this equation. Thank you listeners for listening, like paying your attention towards my PPT, and thank you one and all. And you can, like if you want, you can download my PPT from my link in the description.